let's wait a minute or so.
I see. So you had to had an extra button to start the webinar. I didn't know that.
Yes, yeah, because I programmed it like that.
Right.
No, so that we have a few minutes to get ready before we start, and then we go live. And now let's wait 1 minute, and then we can start. Okay, I see Robert is in the list of participants, so maybe if he wants to join us on the panel, we can ask him to join us just now. Okay, I think now I stop sharing the screen, and it's time to introduce. Okay, let's start. Good afternoon, everyone. Welcome to this edition of the NITheP Colloquium. My name is Francesco Pedruccione, and I have the pleasure to introduce to you today Sanjaye Ramgoolam. If I'm not mistaken, he's originally from Mauritius, yeah, and I think we even met there on one occasion. Yeah? And but at the moment, he's based at the Queen Mary University of London, where he's in a postdoc at Princeton and at Brown University. And he's associated as to WITS as a kind of I don't remember as visiting professor. Sorry, I forgot. So that she has a stronger relationship to South Africa, and his work also with many colleagues at WITS. So Sanjay, I'm very happy that you're with us today, and I'm even more happy that you're speaking with something that starts in the title with quantum mechanics, yeah. which is more up my alley than the usual energies that you guys usually deal with. Yeah. Okay, Sanjay, I don't know if you are ready. You can start sharing your screen. And while you do that,
I'll do that.
I will introduce Ilya, who kindly agreed to moderate a question and answer session. And please, if you have questions, make use of the Q&A facility at the bottom right of your Zoom screen. Yeah. So Sanjay, we can see your slides. Yeah, perfect. So
great.
If you are ready, you are welcome to start.
Okay, perfect. Thank you very much, Francesco. Yes, very happy to be speaking about quantum mechanics on combinatoric algebras, tensor models, and Kronecker coefficients. This talk is based on a sequence of papers, the latest one being quantum mechanics of bipartite ribbon graphs. This is this paper in the archive with Joseph Benjeloun. There was a paper a couple of months earlier with Gareth Kemp, a couple of other papers with Joseph, and one with my former student, Paolo. So all the references are there. So let's start with quantum mechanics. In quantum mechanics, we are doing physics with a Hilbert space, which we're going to call H. And we're interested in something very simple to begin with, finite dimensional state spaces. For example, the spin states of one electron or a many electron system. These are all based on a Hilbert space, which is finite dimensional. And so what is our Hilbert space? It's simply a finite dimensional vector space equipped with an inner product. So given elements of our Hilbert space and a complex number, these are the things we can do. We can add vectors to get other vectors. We can scale vectors to get other vectors. We can take a scalar product, which takes two of these vectors and gives you a number. And there are various consistency properties between these different operations. And when we're talking about, what we'll be talking about here is a Hilbert space, or different examples of Hilbert spaces, with some additional structure. and the additional structure is an associative multiplication. So given our vectors, which we could add, scale, and take scalar products before, now we have another product. Given two of these vectors, we will be able to get another element of the vector space. Okay, so this multiplication will be associative, and because we have a vector space with an associative product, so vector space with an associative product, that's what is called an associative algebra, or algebra for short. But here we also have, because it's a Hilbert space, we have a non-degenerate inner product on that vector space. So if you like, we have a Hilbert space algebra. So we're going to be thinking about Hilbert spaces which have an algebra structure, and also we'll have in many of the examples, in the few examples that we'll be talking about, Hilbert space H will have a distinguished basis of vectors, a set of basis vectors which have kind of a distinguished geometric and combinatoric meaning. So we're kind of just doing quantum mechanics where the Hilbert space happens to have some extra structure. Because the quantum mechanics, the Hilbert space is finite dimensional, we're going to have some finitely many, let's say 1 up to m basis vectors. And because it's an algebra, we can multiply them. I called it star before, probably I should call it star. Multiply two of them, you get something else which lives in the Hilbert space. So it's a linear combination of the vectors themselves. Okay, so given basis vectors R and S, you have some structure constants, and then you get back the vectors. And these numbers will have some interesting properties. These structure constants will be non-negative integers in the geometric basis that I mentioned. And there will be interesting Hamiltonians which are solvable. So we'll be able to make some exact statements about their eigenvalues and the degeneracies of those eigenvalues. So there's an interesting sort of interplay between different disciplines in the story I'll be telling you. So I just want to highlight that interdisciplinarity here. So the algebras that we're going to be considering come from group theory. They come from the symmetric group Sn, and there's a group algebra, which is an algebra of the kind I defined before, associated with a group. And we're going to be taking, in case 1, the Hilbert space to be the group algebra of Sn, and also a simpler algebra related, which is called the center of the group algebra of Sn. So I'll be talking about the group algebra of Sn and the center of the group algebra. And we will be getting some nice interpretation of kind of familiar results from group theory in terms of Fourier transforms on this Hilbert space. That will be part of how I will start the talk. And then also in the story, there will be another algebra that comes up, which is related to Sn, but it's related to triples of permutations. You have 3 permutations, then you do something with it, and then you do some, using the idea of algebras, we can do some non-trivial things. In fact, we will be able to give one answer to an open question in the group theory of Sn. And then we will argue that designing quantum computation experiments based on these quantum systems in the lab will be interesting for computational complexity theory. And the reason that comes about is that the eigenvalue degeneracies that come up in this case too are related to questions which are computationally hard and are called NP hard questions. There's kind of an interaction between group theory, theory of algebras, quantum computation, and complexity theory. So, and another element of interdisciplinarity in this story here is that these algebras that I'll be talking about, the one related to triples of permutations and other related algebras, have been actively studied in theoretical physics in recent years because of their role in quantum field theory and string theory. So that's yet another discipline that is involved here. in a very important way. In particular, gauge string duality is involved, which is just a correspondence that relates physics of string theories to physics of quantum field theories that look apparently very different. So we have correspondence between two-dimensional strings and two-dimensional quantum field theory. This is the string theory of two-dimensional Yang-Mills. We have 10-dimensional strings and 4D quantum field theory. And we have tensor model holography, which is another example relating different kinds of stringy and other things which are not manifestly stringy. So in all these different examples of gauge string dualities, algebras such as this have been playing an interesting role. And so I will be talking about how this interplay happens. That'll be part of the story I'll be telling you. Okay, so here's the outline of the talk. I'm going to start with a review of the symmetric group Sn, just to introduce some notation and to define exactly what I mean by the group algebra here and the center of the group algebra. So here there will be a group and there'll be some related algebras. And then I will introduce representations and Young diagrams, which are used to describe representations of symmetric groups. And we're going to look at representations and Young diagrams, and we're going to see how they lead us to understanding of Fourier transforms on these algebras. So a lot of results from group theory can be understood in a fresh way using the idea of Fourier transforms on these Hilbert space algebras that we just discussed. In the third part, I will explain how permutation algebras arise in gauge string duality. And there will be two algebras that I will focus on. One is the center of group algebra of Sn. The other one is this K of n, which I mentioned before. And these algebras show up in the one matrix and the tensor model, respectively. And then what we'll find while studying this algebra in tensor models is that tensor models are related to a very interesting quantity in group theory called Kronecker coefficients. And by looking at the counting of tensor models, of some physical questions in tensor models, we arrive at some insights into Kronecker coefficients, which give a hint about a problem called the constructibility question of Kronecker coefficients. So then I will explain what that constructibility question is, and then how the notion of quantum mechanics on the algebra K of n can be used to understand that, or to give an answer to that constructibility question. So this is quite technical stuff, the last part. So I will actually just introduce the idea today, the key ideas, using simply Hamiltonians on the simpler algebra, which is the group algebra of Sn. And then the bigger story is an elaboration of this basic idea of using Hamiltonians on interesting combinatoric algebras. So if you want to stop me in the middle of the talk, please feel free. I'm happy to take questions either in the middle or at the end of the talk as well. So the symmetric groups. Symmetric group Sn is the group of permutations of all of n objects, which you can take to be 1, 2, up to n. So just all the n factorial rearrangements of that. Here's one, for example, S3. You are permuting three numbers, 1, 2, 3. There are 3 factorial rearrangements. So there are 3 factorial group elements, which is 6 group elements. And you can write the rearrangements in this way, which is called the two-line notation. You start with the standard arrangement. In all these cases, I start with the standard arrangement at the top, and then I rearrange. Either I don't do anything, which is the trivial or identity permutation, or I could do a swap. 1 and 2 are swapped here, and here you have 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1. And there's a total of 6 possibilities. So there is a very useful way to write permutations, which is called the cycle notation. So the identity permutation, which was 1 is being mapped to 1, 2 is being mapped to 2, and 3 being mapped to 3, in cycle notation, you just enclose them in a cycle separately, 1, 2, and 3. The swap, for example, which takes 1 going to 2 and 2 going to 1, I put them within a cycle, and the number 3, which is left fixed by this permutation, is in a cycle of its own. And the 1, 2, 3, so here's the, in all these cases, you have a cycle description of the permutation. For example, if you have the permutation sigma 5 here, 1, 2, 3 is being rearranged to 2, 3, 1. So 1 is going to 2, so you write a cycle with a 1, and then the 2 next to it, which indicates 1 is going to 2, 2 is going to 3, so 2 goes to 3, and then 3 is going to 1. So I draw a cycle of length 3. So you can think about permutations as maps. You can think of them as two-line notation or in cycle notation. There's also a very nice way to think about permutations in terms of diagrams. So the identity permutation, which is a 1 goes to 1, 2 goes to 2, 3 goes to 3, you line up the numbers 1, 2, 3, and 1, 2, 3 here, and then you have a diagram that takes 1 to 1, 2 to 2, 3 to 3, and a diagram here for sigma 5, for example, 1 goes to 2, 2 goes to 3, 3 goes to 1. So you can draw these diagrams and think of them as permutations. So good thing about cycle structures is that they are conjugacy classes. So there were 3 different cycle structures. By cycle structure, I mean, you just look at what kind of cycle I have. For the identity permutation, I have 1 cycle, or 3 1 cycles. For the swaps, I have 1 2 cycle and 1 1 cycle. And then I have permutations with 1 3 cycle. So this description doesn't keep track of the detailed permutation, just of the structure of the cycles, how many cycles there are, how many numbers inside each cycle. So nice fact about symmetric group Sn is that whenever 2 permutations, sigma 1 and sigma 2, are conjugate, so they're related by an equation like this in the group, then they must have the same cycle structure. Conversely, if they have the same cycle structure, they must be conjugate. So cycle structures are conjugacy classes. Okay, so this is a nice group theoretic thing in terms of group multiplications. And this is a nice combinatoric thing in terms of structures of cycles. So that's permutations and conjugacy classes. What about the group algebra? Well, permutations can be multiplied. In fact, when you just essentially permutation is a map, right? So you want to take 2 permutations to work out what that is as a map from the numbers 1 to n. You just apply the first permutation and then you apply the second. That's the way to define the product. This product is associative. That's one of the group axioms. So what is the group algebra? Okay, so this is the group itself is a finite dimensional thing. There's only n factorial things there. The group algebra, now we just allow ourselves to start considering arbitrary, formal, linear combinations of these 6 group elements in the case of S3. So you have 1 complex number in front of each permutation. You just take these formal sums. Any such thing is said to live in the group algebra of S3. So how many numbers do I have here? There are 6 numbers. So this is a vector space, complex vector space, which is 6-dimensional. And so that these linear combinations, if you have 2 of them, let's say I've just taken a simple case here, 2 of these permutations with some arbitrary coefficients, I can multiply them. I want to multiply this with that, so this multiplication distributes. So essentially I can multiply sigma 1 with sigma 1, 1 with 2, 2 with 1, 2 with 2 with, and I carry along the coefficients. So that's a vector space and it's an algebra. And it's associative because the underlying group multiplication is associative. So now I have an associative algebra. So an algebra is a vector space with an associative product. So now we have that. Okay? And we have a very interesting algebra which is related to permutation groups. Now, this algebra also has a very interesting inner product. So the sigmas are the permutations. And there's a very interesting inner product which just says that I'm going to put in an inner product on this space where each of these permutations is an orthonormal vector, orthonormal basis vector. So the inner product is 0 unless the two permutations are the same. And when they are the same, I get exactly 1. Slightly different way to write this, you introduce a delta function on the group, and you take a product of sigma 1 times sigma 2 inverse. The delta function on the group is defined to be 1 if the group element is identity and 0 for sigma not identity. So this is just saying sigma 1, sigma 2 inverse is identity, just to say another way of saying sigma 1 equals sigma 2, which is what is expressed by this delta function. And this is what you define the inner product on these basis elements to be. And then you can extend this to arbitrary linear combinations by linearity, essentially. So this is a very interesting inner product, it'll turn out. So this is therefore a Hilbert space, which is also an associative algebra, which we can call a Hilbert space algebra. Now, this is an associative algebra. It is also generically non-commutative because Sn is non-commutative. But whenever you have an algebra, you can ask, what is the subspace of elements in the algebra which commutes with all of the algebra? So this Z of the group algebra of Sn is the subspace which commutes with all of Sn and hence all of C of Sn. And that subspace which commutes with everything and therefore with itself is a commutative subalgebra, which is called the center. Turns out the center of the algebra, the Z C of Sn, has a nice description in terms of conjugacy classes. How do I find the subspace? So C of Sn is an n factorial dimensional space. I have an interesting subspace here. And how do I describe that subspace? Well, if you take any conjugacy class, which corresponds to a cycle structure, such as 2, 1, you take all the permutations in that cycle structure, with that cycle structure. So either you can swap 1, 2, or 1, 3, or 2, 3. You add these permutations, and then you can just work this out. If you multiply on the left with any permutation in S3, or you multiply on the right with any permutation in S3, you'll get the same thing. This is a central element. It commutes with everything. So conjugacy classes or cycle structures are described by partitions, different ways of taking the total number, which here is 3, you split it into 2 plus 1. So in general, different ways of splitting are called partitions. And let's say TP is a sum of all the permutations in the conjugacy class given by the partition P. So it turns out these TPs give a basis for the center of the group algebra. So any element in group algebra of Sn which commutes with everything can be written as a linear combination of these central elements associated with conjugacy classes. Great, so that's all I wanted to say about the group and the group algebra. So if there are any questions, I'm happy to take any questions, but if not, I'll continue. Okay, so we have the group and the group algebra, and we have the center of the group algebra. Now we're going to look at representations and Young diagrams. So irreducible representations of the symmetric group can be enumerated using Young diagrams. A Young diagram with n boxes is described by a sequence of positive integers, r1, r2, ... such that the sum of the r's is equal to n, r1 is greater or equal to r2, and so on. And there are 3 Young diagrams for S3. So there are 3 ways of writing the number 3 as a sum of positive integers. If 3 equals 3, this is a Young diagram with a row length 3. 2, 1, we have a row length 2 and a row length 1, and so on. So as you can see here, the number in this example, there were 3 conjugacy classes and 3 representations. So this is a general fact about groups. The number of irreducible representations is equal to the number of conjugacy classes. Then the dimension of the representation can also be computed using a simple combinatoric rule associated with putting some numbers in the boxes of the Young diagram and calculating a simple ratio, and you get the dimension of the representation. Different labelings of Young diagrams with the numbers 1, 2 up to n can be chosen. And for each labeling, they can be chosen according to some rule. And for each allowed labeling, you have a basis vector for a vector space VR, whose dimension is this dr. And this is a representation. So that means for every group element, we have some linear operators which map from the vector space back to the vector space. So in this case, you can concretely think of the vector space as being given by linear combinations of labeled Young diagrams. So good. So we have some linear operators, and you choose some basis, you get the matrix elements. And because this is the dimension of this representation is dr, the matrices are arrays of size dr times dr. Now, the matrix elements, if I keep r, I, and j fixed, and I vary sigma, they are a set of functions. For each r, I, j, I have a function of sigma. And how many total number of functions do I have? Well, there's dr square of them. So if I sum over all Young diagrams, I get n factorial. And this is a nice fact about group theory, which relates the order of the group to the e-reps. So we can interpret these facts about group theory in terms of the group algebra. So specifying an element of the group algebra involves specifying a linear combination. And there is, as we said, an n factorial dimensional space here with basis given by the permutations. You can also write a linear combination like this using these drij's, these matrix elements in irreducible representations. So here you are summing over all sigmas, and the weight is drij of sigma. And this combination, we're going to call it qrij. So this is a new basis, which is labeled by Young diagram and states. And this identity tells us that the basis elements on the two sides, the number of them is equal, as it should be. And there's some nice identities obeyed by these matrix elements. If I choose a nice orthonormal basis, which is group invariant, and we can use the reality of the representations, and there are some very nice identities that these D matrices obey. Using those identities, you can multiply these Q elements of the group algebra. And here's very interesting thing about the Qs. When you multiply them, they are labeled by Young diagrams and then some state labels. What happens when you multiply them? You get 0 unless the Young diagrams are the same, or S, unless R equals S. And then you get a delta JK delta QIL. So this structure of deltas and Qs is like the multiplication of elementary matrices. And essentially what this is telling us is that the group algebra of Sn is isomorphic to a direct sum of matrix algebras. So there are different blocks labeled by R, and for each R there is dr square elements, which you can think of as being organized in a square block of size dr. And we have, of course, a nice inner product. Turns out that these facts are examples of a very interesting Fourier transform. So where we have these QRIJs and we have permutations, and these are Fourier coefficients which relate these guys to these guys. And whenever you have Fourier transforms, you have a nice delta function, formula for the delta function in terms of these coefficients, and there's an analogous formula for the delta function on the group in terms of characters. So I talked about Fourier transform on the group. There's also a Fourier transform for the center of the group, which is you just take the sum over I and j. You set I equals j and you sum. You set I equals j, you sum, That gives you this quantity, which is expressible in terms of characters. And now we have a Fourier transform between the projector basis of the center and this conjugacy class basis. So essentially, we can think about representation theory in terms of Fourier transformation on these algebras. And this story that we just saw is a rather general story that holds for many, whenever you have an associative algebra with a non-degenerate inner product, something called the Wedderburn-Artin theorem, which says that such algebras are isomorphic to direct sums of matrix algebras. In the case of the group algebra, the different simple matrix algebras are labeled by Young diagrams, and the size is dr. For the case of the center, again, the blocks of this the matrix blocks are labeled by Young diagrams, and the size is 1. So essentially, group theory and representation theory gives us a matrix decomposition of these algebras. Now, these kinds of matrix decompositions of algebras can be generalized to various algebras related to the group algebra. And such algebras have been identified and studied in detail, in different examples of gauge string duality in the past 25 years. 2D Yang-Mills, ADS-CFT, matrix models, tensor models, and so on. And different instances of gauge string duality have been uncovering different instances of such algebras and mapping out how different physical questions sit inside these algebras. So part 3, I will talk about how these permutation algebras arise in matrix and tensor models, which are relevant to gauge string duality. Okay, so I'm going to start with a one matrix model. So Z is an n by n complex matrix. Partition function is integral dz e to the minus trace z z dagger. There is a unitary symmetry. Z goes to u, z, u dagger, where u is a unitary matrix. The interesting observables for physics in this model are the holomorphic gauge invariant polynomial functions of Z. What do these things look like? If you have degree 1, the gauge invariant thing is trace Z. Degree 2, you have things like this. And degree 3, you have 3 gauge invariant. As we saw before, there were 3 conjugacy classes in S3. And the connection between polynomial functions and S3 or Sn in general is not an accident. And the way to see the precise connection is to think about how these traces are written, these gauge invariant functions. For example, trace Z square in index notation is just that. Trace Z square is this one. And what's happening going from here to here is that here you have I1, I2, here you have I2, I1. So you are getting different observables, different functions from different permutations, either the identity or the swap. In general, you can take Zs and you have a bunch of indices above, and this is I1 up to In. And the same indices should appear below, except in some arbitrary order, if the function is going to be gauge invariant. And so you have an observable labeled by a permutation. And it is simple to show that if you conjugate the permutation, you get the same observable. So for n, where the degree of the thing I'm thinking about is less than capital N, the number of such linearly independent degree n polynomials is equal to the number of conjugacy classes of Sn, which is the dimension of this algebra, the center of the group algebra of Sn. And that number, I'm just going to call it P of n. And for each of these partitions of n, there's a conjugacy class, as we said, and there is a central element. And what we are saying now is that correspondingly, you have sum over all permutations in a fixed conjugacy class. You can take the sum over all permutations of these observables that we defined, where the indices are contracted according to that permutation sigma here. Okay, so I can, if I kind of add another sigma, which is in the same conjugacy class, I get essentially the same observable. So I can just take an average to get something labeled by not permutations, but by partitions. Change of basis, just apply change of basis in the group algebra to go to the Young diagram basis. and you get characters, and you take a sum of these observables labeled by partitions. And this new basis was used in ADS-CFT to compute correlators, which are integrals involving these different observables. And there's a very nice story about what happens at finite n, which is not too important right now. But the key point is this algebra. To understand the one matrix model, a lot of the physics in the one matrix model is in this algebra, in understanding the different bases, the base labeled by conjugacy classes and the basis labeled by Young diagrams. And if you understand the connection between the two, you can do various calculations of correlators. This story generalizes to tensor models, where instead of having matrices Z with one upper index, one lower index, now our variables will have three lower indices and a conjugate one with three upper indices. And this is the model in question, which was studied actively in the tensor model community. And you have Zijk, Z bar ijk. This is a model where we have a UN cross UN cross UN symmetry. These transform in the fundamental, tensor fundamental of UN, and these are the conjugate representations. And what is interesting for the physics here is observables which are invariant under this product group. And there is a nice combinatoric way to think about these observables. For each of these Zs, sorry, I have called the Zs phi in this diagram. For the Zijk, I have a vertex with three kinds of edges, color black, blue, and red. And I have for the conjugate variable, I have another vertex with three colors of edges. And for a gauge invariant thing like this, where I goes to I, j goes to j, k goes to k, I can combine this diagram and produce a colored graph. And in general, if you want to look at an observable of degree n, essentially for it to be gauge invariant, I have to have the same number of Zs as the number of Z bars. Let the number be n. So I have I1, J1, K1 up to IN, Jn, Kn, and then I1, J1, K1 up to IN, Jn, Kn, except in arbitrary reordering. Because I have UN cross UN cross UN, so I'm treating these three UNs as separate symmetries, and I want invariance under that symmetry. The upper I index must be contracted with one of the lower I indices, the upper J with one of the lower J, upper K with one of the lower K. So there are three permutations. So you can draw your n vertices here and n conjugate vertices. There's some permutation that mixes up the black edges, some permutation sigma 2 for the blue and 1 for the red ones. So one can show that if you have these three permutations, again, there is an equivalence. Not all distinct permutations give distinct observables. If you multiply on the left by the same permutation gamma 1, or you multiply on the right by the same permutation gamma 2, you get the same observable. So this tells you that we're thinking about the group Sn cross Sn cross Sn, modulo on the right by the diagonal subgroup and the diagonal subgroup on the left. So that's a nice generalization of a coset. It's a double coset. So using that picture, you can count the number of tensor observables, count it as a function of n. Because of this Fourier transform idea, there are two ways to count it. One in terms of partitions, one in terms of Young diagrams. When you count it in terms of partitions, you get a kind of a symmetry thing associated with each partition. And this one is a representation theoretic thing associated with each partition. So P here refers to cycle structures of permutations. And when you have a permutation with, let's say, P1 cycles of length 1, P2 cycles of length 2, P3 cycles of length 3, and so on, there's this quantity made out as this vector quantity P, which is called the symmetry of the cycle structure. And to count the number of observables of degree n, you just sum and you find the sim P. You weight the sum by this quantity sim P. Another way to count it is to look at representations VR1 tensor VR2 tensor VR3 of Sn. And as usual, when taking tensor products in quantum mechanics or multiparticle systems, we take the group element acting simultaneously on all three. And you let the group elements act this way, and you decompose this into irreducible representations. Okay, if you like a Clebsch-Gordon decomposition. And you ask how many times does the trivial representation of Sn appear? Okay. And that is called the Kronecker coefficient. So the counting of tensor observables is also related to the sum of squares of Kronecker coefficients. Now, this is very interesting because there's something called a constructibility question in the mathematics of Kronecker coefficients. And the fact that tensor models, the counting of tensor model observables, which we said is a counting of graphs, which is a very concrete combinatoric thing, is related to Kronecker coefficients by this formula. And this sounds relevant to the constructibility problem. So what's the constructibility problem of Kronecker coefficients? Let's just explain that problem. We know that Kronecker coefficients, from the group theory definition that we gave, can be written in terms of a sum of characters. So in general, for n large, n factorial is a complicated sum, but it can be expressed in terms of this is R1, R2, R3. So it can be expressed in terms of characters. Now, each of these characters has a nice combinatoric construction. What does that mean? It means that to find for a given Young diagram R and a given conjugacy class P, what is the character? There is a formula of this form where I sum over T is a kind of labeling of a Young diagram. It's called border strip tableau for the Young diagram R and the conjugacy class P. This T is actually P, sorry, this is P. So there's a kind of labeling of Young diagrams you can define. And the rules for the labeling depend on the Young diagram, and they depend on the conjugacy class. And then there is a formula for the character in terms of counting those labeled Young diagrams. So you count those labeled Young diagrams, you sum them up either with a plus or minus sign, you get a quantity, that's the character. So that's an example of something which is very constructible. There's something you can build, you can count them, and you get a number, which is the integer of interest. There's also in group theory something called the Littlewood-Richardson rule. This is a number associated with a triple of numbers, 3 Young diagrams with n, m, n plus m boxes, also expressible in terms of characters, and it has a nice combinatoric rule, labelings of Young diagrams and such. No such rule is known for the Kronecker coefficients in the case of general R1, R2, R3. There's some partial results in some special cases of Young diagrams. You can find that in some recent mathematics literature. So you see, we have a number which we know is 0 in general. We know it's either 0 or positive. It's a non-negative number. It's expressed in terms of characters this way. Each term in the sum could be either 0, negative, or positive, but somehow it all adds. And there's also a factorial here. So some of these will be rational numbers, but it all adds up to something which is non-negative number. So why is that? Okay, so there's no simple interpretation. There's no thing you can build using Young diagrams in any obvious way that gives you a Kronecker coefficient. But tensor models are teaching us something very interesting. They are teaching us that if you sum C square over all Young diagrams with n boxes, you get something which is the observables of a tensor model of degree n. And for each observable, you have a colored graph. That's a constructible thing. So we're learning that the sum of C square is constructible. So if only we could select from this sum the one term that corresponds to a triple, then we would be able to say something about constructing the Kronecker coefficient itself. So the question we asked in this recent paper was, can we refine the combinatoric construction for the sum to give a combinatoric construction for an individual Kronecker coefficient. So, and the way we approach that question is we observed, this is also an earlier result, that associated with the counting, there was a double coset there, Sn cross Sn cross Sn, modulo diagonal Sn on both sides. Well, it's actually known that when you have double cosets of the form G mod H on the right, mod H on the left, then associated with that double coset, there's an associative algebra. So there's an algebra called K of n, and the detailed study of that algebra, what does a Fourier transform look like, how does that teach us about tensor model correlators, that was in my paper with Joseph from 2017. So now the question we were asking, how can we use this algebra, in order to refine this quantity and say something about the particular Kronecker coefficient. So I'm not going to, because it's a little bit technical, but the main idea is actually very simple. And I'll talk about the main idea in terms of the ordinary group algebra. So I'll explain the main ideas shortly, but the outcome of that discussion is the following. So we use the idea of Fourier transform on this algebra. Again, this is an algebra which has a nice combinatoric basis related to graphs, these kind of colored graphs I was telling you about. It also has a Fourier basis in terms of Young diagrams, in fact, triples of Young diagrams. So in this algebra, there's a basis which consists of things like Q, R1, R2, R3. Alpha goes from 1 to C square, where C is the Kronecker coefficient. Now consider this combinatoric basis, one basis element for each graph. Think about the space of all linear combinations of these graphs. Well, the total number of these graphs, which is a counting of tensor model observables, I'm going to call curly n of little n. And these are real numbers. I'm going to think about real combinations. That defines a Euclidean space. In this Euclidean space, if I restrict the a's to be integer, I get a lattice. And that's the integer lattice of that same dimension. So what we found was that inside that integer lattice, there exist sublattices of dimension equal to C, R1, R2, R3 square. And for each triple, a basis for the sublattice can be obtained by looking at the construction, of the null vectors of an integer matrix. So the null vectors of an integer matrix are integer vectors. And these integer vectors describe integer linear combinations of the basis vectors, which are these graphs. And as a result, we have a concrete algorithm to construct the sublattice whose dimension is C square for a given R1, R2, R3. To explain the main ideas in arriving at this, I want to explain how the ideas work in a simpler case of just quantum mechanics on the group algebra. So here's a combinatoric algebra. It has a combinatoric basis of permutations, sigma. Nice combinatoric objects, there are pictures associated with it, and there's a Young diagram basis, QRIJ. The center has a combinatoric basis consisting of these sums of permutations in a given conjugacy class. Kind of distinguished among these are those permutations which have just a single non-trivial cycle, length 2, length 3, up to length n. So I'm going to call them T2, T3, up to Tn. So it was shown recently in a paper with Gary that if you take just the T2 up to Tn, so there's n minus 1 of them, which is much less than P of n, which is the dimension of the center. If you take these guys and you take their sums, and sums of their products, you can get the whole of the center. And in fact, generically, only a subset of these n-1 things suffices. If you just take the sum of permutations with one non-trivial cycle of length 2, you can generate, and take its powers and linear combinations of such, you can generate the center for Sn for 2, 3, 4, 5, 7. If you take T2 and T3, you can generate the center for up to 14. For T2 up to T6, you can generate up to 79. So basically, for any Sn, there is a number k star, such that if you take T2, T3 up to Tk star, you can generate the center. So these Tks are very interesting. You can act on sigma. That means multiplying the sum of permutations with a permutation and just looking at what other permutations arise. This defines for you a matrix, which depends on k, and it's the basis labels are sigma and sigma prime. So that's an integer matrix. A given sigma either doesn't appear or it appears with some multiplicity. It's integer, in fact, positive. So here's an integer matrix determined by the combinatorics of multiplication of permutations. The C of Sn also has a Fourier basis, Qrij. What happens when Tk acts on Qrij? You just get the character for that conjugacy class divided by dr, so the character of the sum of elements in that conjugacy class. So you get this normalized character times the Fourier basis element. So the Tks themselves define, you can show, Hermitian Hamiltonians on this group algebra using the inner product that we defined. And their eigenvalues, they are known combinatorially. These things are known from this Monahan-Nakayama rule. So they are rational numbers. They are known combinatorially. Of course, given a Tk, you can, if you act on a Q, you'll get some rational number here. It is possible that for a given Tk, two different Qs, R and R prime, might give you the same normalized character. However, if you take T2, T3 up to Tk star, that distinguished thing which generates the whole center, then you take the normalized character of those guys, that set of numbers is sufficient to distinguish the Qs. Once you have a certain set of eigenvalues for these guys, you know exactly which Q you're talking about. And you can also show that if you take a linear combination, A2, A3 up to AK star, where these are themselves integers, the eigenvalues of this Hamiltonian will also distinguish Young diagrams. So if two Young diagrams, so the eigenvalues of that can be shown to distinguish Young diagrams. And what are the eigenvalues? Well, this is related to T2, T3, and so on. So A2, this rational thing, A3 times this rational thing, up to AK star, that's a typo, times this rational thing. So the eigenvalues of the Hamiltonian are some rational numbers, which are determined in terms of normalized characters. Okay, so we have a Hamiltonian, we have a Hamiltonian corresponds to a matrix in a basis. I act on the permutation basis, I get an integer matrix. So there's an integer matrix corresponding to M on the permutation basis. M minus lambda R is another linear operator. And lambda R, I know that's some input I'm going to use. It's a combinatoric input. It's known normalized characters. So I'm looking for vectors where X or where M gives you lambda R. So that means if I look at M minus lambda R times the identity and apply that to those vectors, I will get 0. So the null vectors of this matrix are integer linear combinations of sigma, which are precisely belonging to the subspace labeled by a fixed R, because I have constrained the eigenvalues to be the ones for that particular R by choosing my Hamiltonian minus lambda R. So that's now a rational matrix, and I'm just looking for the null vectors of that rational matrix. So turns out that if you're looking for null vectors of a rational matrix, it is known that those vectors themselves are can be chosen to be integer vectors, and they correspond to integer linear combinations, in this case of sigmas. And how many of them are there? Because they belong to the sector labeled by R, there's exactly dr square of these null vectors. So this gives you a combinatoric construction of the number dr square. Why is it combinatoric? Because the m essentially came from multiplication. The m came from the t's were multiplying sigmas, and these were the matrix elements of that multiplication. So you have an integer matrix, and you're trying to find the null vectors, and they're very nice constructions of these integer vectors, which form the null vectors. And good, so this gives us a combinatoric construction of dr square. Of course, dr square, there are other known combinatoric constructions which are easier, but this illustrates the main idea. And the question I will end up with, well, the summary is that quantum mechanics on combinatoric algebras such as group algebra of Sn or K of n is very interesting. Question we can ask is, can we realize these kinds of quantum mechanics systems in the lab and use them for quantum computation? And the question of, I mean, some of these questions are related to K of n, which is related to Kronecker's, and deciding the vanishing of a given Kronecker for large n in general is a computationally hard problem. So quantum computations with quantum mechanics on these algebras would be very interesting. So I'll stop here.
Okay, Sanjay, thank you so much for the very interesting talk. I see, Ilya, that there are a few questions in the chat.
There was a kind of clarification question in the chat, but I think it went a little bit later than it was necessary to be asked. So that was about the very, very first part where you introduced the algebras. And the question is, yes. Thank you for the nice explanation. Is it a sigma algebra as well? I don't know.
So I don't know what a sigma algebra is. Can you clarify?
I don't know. That user has not. Can probably clarify his question in Q&A section. And can I ask a question?
Yeah.
You kind of, in the end, you introduced this very nice approach to the kind of quantum mechanical Hamiltonian, but do you have any examples of like what kind of Hamiltonians, you know, one would expect to see? Is it kind of spin chains, or what kind of physical systems are you going to see? Or it's spin chains with a certain locality properties of what we're talking about?
So I guess, you know, the question of, I think that relates to the question at the end, you know, of how can we simulate such a system? And if you have a spin system, I guess, you know, you have 1 up to, let's say you have n spins. So in that you could permute spin 1 and 2. So in this Hilbert space where your state space, there are the spins of n objects, you have permutation operators. But I think but you want to sort of faithfully represent the permutation operators so that you're really studying intrinsically what the permutations are doing. So, I mean, I don't have a concrete physical proposal for what the system should be, which will realize this thing, but we've just defined the Hilbert space and identified some interesting Hamiltonians in that space, which I think that's sort of an interesting physics question, how to realize these Hamiltonians.
Okay.
In a faithful way.
Okay, and yes, and the person who asked the questions and the clarification is that the sigma algebra, it is closed under the complement and it's closed under the countable unions.
Yeah, it's a very nice algebra because, you know, I think that will be the case because it's just a finite algebra. You know, it's group algebra of Sn, there's n factorial. So yeah, it's finite. So I don't expect there'll be any issue with countable unions or non-closure. Yeah, these are very nice finite algebras. One of the nice things about, the connection between these algebras and tensor models or matrix models is that when you make that connection, then you're not just interested in one of these algebras, like, cent of Sn. You're interested in cent of Sn, cent of S2, S3, S4, a whole tower of algebras. So in these tensor models, matrix models, or associated quantum field theory problems, you have a tower of algebras. So this is a nice instance of quantum field theory where it is being reduced to finite systems, but a whole tower, an infinite tower of such finite systems. And a lot of interesting stuff happens within each finite system, which is the focus of the present talk. But there's also other things that happen mixing these different ends.
Okay, thank you. And there is a raised arm, and I will allow the person to talk, and the person can ask his question.
Yeah.
Sorry, you need to unmute yourself, and you can ask your question.
Please.
Hello.
Hello, Antal.
Oh, hi, Sanjay. Very nice talk. So this gives an interesting class of Hamiltonians.
Yeah.
And, usually we are familiar with the situation when eigenfunctions are characters.
Yeah.
But you have eigenvalues as characters, as far as I understand.
That's right. Yeah.
What is, people already asked questions about the Hamiltonian. What is the symmetry group of the Hamiltonian? Is there a group? Is there a symmetry?
Somehow, we are using the algebra as the Hilbert space. The main role of the algebra is to be the Hilbert space, and the Hamiltonian is an element in the algebra which is central. So it commutes with the whole algebra. So in a sense, you could say the whole algebra is the symmetry, because the whole algebra commutes with each of these Hamiltonians.
Ah, okay. So it's a very, I understand. And the states would be irreducible representations of that symmetry, the standard. We are used to having Hamiltonians with a symmetry group.
Yeah. So in this case, it's a particular, if you like, So the state space is sort of the group algebra itself. And that state space is also decomposable according to irreducible representations. So these were the QRIJs. Those were kind of the representation basis of the state space. In a way, what's the key thing that's going on here is like a state operator correspondence. The whole state space is the algebra. The operators come from the algebra. They act on the algebra because it's an algebra. So by left multiplication, algebra element acts on the full space. So it's, a lot of the familiar stuff, just exploiting the fact that the state space is itself an algebra.
Very good. Great. Nice. Very nice. Good to see you.
Yeah, likewise.
Okay. So we've got a comment in the chat from the person who was asking about the sigma algebras, and the comment is, thank you. Then you may wish to look at the quantum probability space. Could be nice link up to your end question about the quantum computation. Okay. So that's it.
Yeah, I'm happy to think about that. Yeah. Happy to,
Okay, and we have answer or question in the Q&A session. So, is it possible to define permutation of infinite number of elements? In other words, is there any chance that this framework could be extended to the infinite dimensional quantum systems?
You see, so in a sense, there is a infinite dimensionality here, but it comes in a very controlled, interesting way. You see, when let me share my screen to just make sure I explain that properly. I'm going to share my screen. I'll go back to the relevant part of the talk there. So when we made this connection between gauge string duality or these different matrix models and here it is. Yeah, so we had these algebras, and then we started looking at this complex variable. Here is the matrix model we're interested in. So we want to compute this integral, and we want to insert functions of z here and then calculate that integral. And this is the kind of thing that comes up in quantum field theory. In fact, this particular problem comes up in the ADS-CFT. It controls the half BPS sector of 4D super Young-Mills theory. So there, the things of interest are these polynomials, so trace z. So here, and the connection between these polynomials is that polynomials of degree n, I1 up to In, are described using permutations in Sn. So this is a finite dimensional system of Sn. But then here, degree 3, we would have S3. Degree 2, we have S2. And then degree 1, we have S1. But we're interested in all observables. So in fact, what's happening here in a lot of these models, we are looking at algebra, which is more like a, so here the algebra of interest is the direct sum n equals 0 to infinity, the center of the group algebra of Sn. And similar algebras, you know, direct sum C of Sn, n equals 0 to infinity. And there's the direct sum, the other one that is relevant for Kronecker's is K of n. So I think what you are asking is somehow S infinity directly. Think about permutations of 1 to any number with no limit. Somehow that hasn't come up in this particular problem. We are instead looking at this kind of infinite things. And a lot of physics is captured by this kind of infinite direct sums.
Okay, thank you. And I think that can it be understood in the following way? For example, if I have a harmonic oscillator, this means that, for example, I'm only going to consider like the subspaces of the fixed number of excitations, but I consider them from 0 to infinity in the full Fock space.
Exactly. Yeah, that's right.
Okay.
Yeah, that's right.
Okay, thank you. I think that's all questions which we have.
Okay, thank you very much. And if we don't have further questions, Sanjay, thank you so much.
Thank you.
Maybe let's conclude with an advert. Yeah, and in fact, you're the object of the advert, because on Thursday, Sanjay offered to give us another maybe slightly more technical webinar on Thursday afternoon at 2 p.m. South African time. So if you would like to learn more about this, please join us again on Thursday afternoon. And there you will have again, of course, another opportunity to ask questions should the questions pop up between now and then. Yeah. So Sanjay, thank you so much for being with us this afternoon and for sharing some of your recent work. Thank you to all the participants for being so loyal and following the talks every Monday afternoon. And Idia, thank you very much for moderating the question and answer session. So Sanjay, thank you very much. Have a good rest of the day in London and stay safe.
Thank you. Thank you very much, Francesco.
Yeah,
Thank you, Ilya. I enjoyed the interaction. Yeah, and just to say that the next talk will be just elaborating, you know, what exactly did we do with in that Kronecker paper, how the last part that I talked about in this talk, how we take that further and apply it to this more complicated algebra.
Okay, that will be very interesting to see. So just 3 days and and we will learn the end of the story, or the end of the story so far. Yeah. Okay, Sanjay, then again, thank you so much. We will see you again on Thursday, same procedure as today. Just it's another time. It will be at 2 o'clock our time, not at 4. Yeah. Okay, then thank you very much, everybody. Have a good evening. Thank you, Sanjay. Thank you very much.
Thank you. Bye-bye.